Hello and welcome to my introductory GSOC 2020 video. My name is Dipankar and this summer I'm going to work with Beaglebone.org on my project titled Parallel Bidirectional Bus. The mentors for this project are Saket, Abhishek, Jason Kridner, Huyun Yao, Drew Fustini and RMA. A little information about me. I am currently studying Masters of Applied Computer Science at Technische Hochschule Deggendorf, also known as Deggendorf Institute of Technology. I have programming background in C, C++, and Python, and my interest areas are embedded OS, embedded firmware, and robotics. So my project aims at creating a reference design for situations where large number of low latency, high speed IOs are required to read data from. Like in case of game controllers, you would like to read a lot of inputs and send them to the PRU for processing in real time, and situations where you would like to control a lot of outputs uh, in real time. For example, in case of LED panels, or there can be other situations like the motor drivers, which require a lot of pins, and the pins need to be bit banged in a special sequence, which is very time critical. So all these situations require uh, high performance, low latency operations in real time. So to achieve my objective, I'm going to use shift registers and I'm going to interface them with the PRUs. And this shift register can be configured in serial in parallel out mode or parallel in serial out mode. So the shift registers that I have chosen to interface are 74HC595, which is a serial in parallel out register, and 74HC299, which is a universal shift register and can operate in both the CPO and PISO modes. So in order to accomplish all the tasks, I need to write one LKM, GPIO chip loadable kernel module, a PRU firmware, some device tree overlays, and some interfacing schematics. Here you can see two very important subsystems of Octaveo's system in package, which is at the heart of Pocket Beagle. As you can see, the main processor is based on ARM Cortex A8 architecture, and it runs a Linux operating system. The other subsystem, called the real-time coprocessor system, consists of two PRU units. PRUs are basically microcontrollers, each of 32 bits and can operate up to 200 megahertz. Unlike the main processor, which runs a Linux operating system, these PRUs are free from the overheads introduced due to the OS and hence are suitable for real-time operations. Here you can see the P1 and P2 headers that you can find on the Pocket Beagle. There are specific functionalities that are available only on the specific pins. For example, SPI0 is available on 6, 8, 10, 12 of the P1. Similarly, the UART0 is available on pin 30, 32 of the P1 header. You can also see that there are some pins which has a PRU label and is colored in cyan color. These pins have the enhanced PRU functionality. In the first glance, one can say that there are 19 pins which has the enhanced PRU functionality, but on a closer look, you can see that these pins are multiplexed. That means they also have some other functions. So for example, if you are using UART0, you cannot use those pins as PRU pins. Similarly, if you are going to use SPI0, you are again going to lose two PRU pins. So in practically, the number of PRU pins can be less if you have a complex embedded system which has some sensors connected to SPI, some UART connected things, and so on. Also, not all PRU pins can be configured as both input and output. For example, on P2 header, the pin 31 can only be configured as PRU input and 33 only as PRU output. So we have a limited availability of high performance PRU pins. It is in such a situation that this project comes into picture. You can see the first schematic of my implementation. Here we are using just 4 PR pins, which is controlling the shift register HC299. And with these 4 pins, we can control 8 um, IOs available on the shift registers. We can take input from these IOs, can shift them inside the PRU, or can connect some LEDs or some other peripherals and control them and give them output. So with just 4 pins, we can have uh, a lot many IOs, which otherwise we can't have. Also, these shift registers can be daisy chained. And with just 4 pins, if we daisy chain one more shift register, we can have an increment of 8 IO pins. So in this way, it helps us to have more IOs which can be scanned in or which can be controlled as output. So here is a block diagram that depicts the flow of information in my application. So first, the user space application will invoke the GPIO chip driver and will pass it instruction or data. Then the chip driver will pass it to the PRU. This can be done using RP messages or writing this information on a specific register from where the PRU can read it. Then the PRU will generate a bit stream accordingly and will send it to the shift register. So right now what I'm doing is the shift register in serial in parallel out mode. So the serial stream will go inside the shift register, and then the shift register will pass them on to the connected peripherals. Here you can see the shift register acting in parallel in serial out mode. Now the PRU will instruct the shift register to scan in the connected peripherals, and then this information will go inside the PRU. The PRU will then pass it again to the GPIO chip driver using RP message or writing to a specific memory area, and then this data through the GPIO chip driver will be available to the user space application. So this way, both a bidirectional communication will be implemented. So finally, I again want to reiterate the deliverables and what all will I do in this. I will be writing a GPIO chip driver, and then it will be interfacing these two ICs and writing the PRU firmware to take input and to pass on the data, and then device tree source to configure the pins on boot. So that was all. Thanks for your attention. Have a nice day.